Okay, good afternoon, everybody, and welcome to part one of Arista's new webinar series. We're going to be covering next-gen service provider technologies. And today we'll be covering the journey to next-gen service provider transport and services. So in just a second, I'll hand over to my colleague Sasso. Just a quick couple of pieces of housekeeping. So today, as I said, is part one of our series. We're also going to be covering Arista service provider building blocks next week, same time, same place. And then on the 14th of July, in 2 weeks' time, we'll be covering next-gen service provider use cases. Just one last thing to mention, if you do have questions, please feel free. We'd love to interact with you, but could you please use the Q&A panel of Zoom rather than the chat window? We won't be able to answer questions in the chat window. With that, I'll hand over to my colleague, Sasso, to take you through today's presentation. Over to you, Sasso.
Thank you, James. So good afternoon. Welcome to this presentation to the journey to next-gen service provider transport and services. My name is Itxaso Igueregi, and I work at the Arista Networks as a systems engineer primarily focused on service providers. This presentation has been brought together by myself and my colleague Guillaume Gotardi and Massimo Magnani, who will be helping out with any questions you raise during the session. Okay, so let me walk you through the agenda. We'll start talking about the service provider market trends, followed by the network services evolution with EVPN, and then transport services evolution with segment routing, finishing with a segment routing demo. Okay, so let's get started with the service provider market trends. We are all aware that the use of smartphones, cloud, and over-the-top services are changing the way technology is being consumed. Traditional internet was driven by web and e-commerce applications used by desktop consumers, where many-to-many connectivity was required. Today's internet use has drastically changed in terms of consumers and content, changing from web browsing to over-the-top services and rich content, social media, video streaming, and online gaming, among others. This trend has been exacerbated during the pandemic, where we've seen unprecedented growth in global internet traffic. Looking at some statistics about application usage after 1 week of lockdown, we see that WhatsApp usage increased over 600%, video conferencing 350%, online gaming 170%, and Netflix over 50%. On the other hand, whereas traditionally there was a many-to-many connectivity, now majority of traffic originates from less than 10 companies: Netflix, YouTube, Spotify, Facebook, you name it. All these changes drive a massive scale and bandwidth requirement. And on top of that, we see that traffic is far more difficult to predict. With software updates, videos that become viral, new Netflix episodes, we see unpredictable traffic spikes. And finally, speed and latency matter for this new content, and thus performance is emerging as a key driver over cost. And we all know that this is not going to stop. We foresee an unprecedented traffic growth driven by AI and ML applications. This internet transformation is changing the fundamental architecture requirements for service provider routing. At the same time, a range of new technologies are now available to carriers that help adopt a number of best practices pioneered in the web-scale community called cloud principles, which are key to staying competitive and differentiate. So let's take a look at what cloud principles can be applied to the routing transformation. Traditional high-scale routing solutions have relied on in-house silicon with 3 to 5 year hardware cycles and highly inflated cost per port compared to the cloud economics in the data center. With merchant silicon faithfully following Moore's law, every new chip generation brings increased forwarding capacity, expanded table sizes, more features and capabilities, and lower power. Also, the use of custom silicon translates into interoperability hiccups because of different hardware implementation amongst different vendors, which may slow down field adoption. Shifting to merchant silicon solves those problems. Another tremendous change, which validates once more merchant silicon adoption, is the adoption of Ethernet plus IP, which replaced the traditional multi-protocol-based wide area network infrastructures. Merchant silicon plus Ethernet plus IP define a clear homogeneous abstraction layer suitable to provide the foundation of any network scenario, regardless the architectural positioning. But there are many more principles on the software side that can be adopted by service providers as well. Visibility is a critical component. Being able to capture what a network is thinking or doing is a basis for the true network automation and analytics. Legacy networking has long suffered from limitations in network visibility, largely due to inefficient polling mechanisms, such as SNMP, that only provide a limited subset of data. As a result, the operators of legacy networks have been essentially blinded when it comes to true network insight. While Arista COS software supports the traditional syslog, SNMP traps, and polling mechanisms for collecting and reporting switch state, these traditional approaches are restrictive when trying to monitor protocol state, environmental alarms, memory buffer, etc. at a sub-second interval. To provide real-time state information, the EOS software also supports real-time state telemetry. With the telemetry data being event-driven, updates can be streamed in real time. This makes the approach vastly superior to traditional polling models that have granularity in order of minutes. Traditionally, network service delivery has always been slow, cumbersome, and based on human operations. Furthermore, not only service delivery, but generally speaking, the whole network operation framework has been performed inefficiently, mostly based on personal experiences and not on automated and repeatable approaches. But if service providers want to be competitive, they must shift to a software-driven model, heavily leveraging automation capabilities to reduce new service implementation time to market and improve network management, control, and troubleshooting effectiveness. These best practices also include an architectural shift from reliance on scaling up increasingly complex and costly legacy routing vendor solution, but instead deploying failure-tolerant, scale-out fabric architectures that can absorb rapid growth in traffic volumes in a capital-efficient manner. These architectures allow a common design pattern to be deployed across the global footprint with any additional physical complexity managed by a fully software-driven infrastructure as code model that allows operators to dramatically improve the efficiency of human operators. Long story short, the whole paradigm must shift from device-centric to network-centric using open, standard-based approaches and software centricity. And all these principles must be achieved with an important driving factor, simplification to be able to automate. So let's take a look at specific service provider networks and how we can apply these cloud principles. Service provider networks have traditionally been built in silos, with totally separate networks for different services, mobile, broadband, business services, all these using multiple proprietary architectures, and with disparate hardware, software, and management solutions, with no operational efficiency whatsoever, making automation and orchestration really hard, slowing down new service delivery and innovation. So how should SP networks look like after applying cloud-native thinking? First, we should build a unique common network that will provide multiple services on top. This network should follow a cloud architecture with an open, resilient, scale-out programmable network. The idea is to obtain consistency and capability parity across robust and future-proof base of standard building blocks using commodity hardware plus value-adding software. This simplicity in software and hardware enables operation efficiency and common automation framework, accelerating service delivery and innovation. So how does Arista fit into this service provider evolution? With our data center foundation, Arista's routing solution applies cloud networking principles of scale out, simplify, software-driven networking to routing use cases. As a pioneer in the networking industry, Arista has long committed to using commercially available merchant silicon from multiple suppliers across its portfolio. Arista has built scalable platforms based on Broadcom Jericho chip suitable for SP networks, which offers 1 gig to 400 gig ports in multitude of form factors with one single operating system. Finally, adopting the merchant silicon model for hardware innovation allows Arista to focus a greater majority of R&D resources on software development and its next generation network operating system, EOS, Extensible Operating System. Arista COS is built on an open source and modified Linux kernel, allowing standard Linux packages and tools to be run on the switch to extend the functionality while making automation easily attainable. The foundation of the proposal is Arista's cloud routing, which marries rich, modern routing capabilities built on standard-based protocols together with modern automation, real-time streaming telemetry, visibility, and programmability to improve operational efficiencies in SP networks. All these delivered with a quality-first approach. So now let's take a look at the technology stack evolution. Technologies have deeply changed in the last 15 years. In the beginning, all the different scenarios had their own set of technologies. For example, WAN and LAN infrastructures were deeply different from the transport technologies, which were not homogeneous for the WAN. Many data links were in use, such as ATM, PPP, HDLC, but they were homogeneous for the LAN, where Ethernet had de facto replaced all the other link layers, such as IPX or token ring. When we come to the upper layer technology, we can say that IP was pretty common in both LAN and WAN, whereas MPLS was very common in the SP market, where it was used to virtualize infrastructure among different end users. In the control and service plane, the situation was a little bit more diverse, mostly because of the kind of services that had to be made available to the customers. Of course, an IGP protocol was needed to provide IP reachability, and BGP started to be more and more used, not only for external peerings, but also to distribute internal routing information. And for transport and services setup, LDP and RSVP have been used to distribute labels, to provide layer 2 services, and traffic engineering. Besides these ones, also BGP started to play a big role in the service area. Indeed, new address families were added to address new capabilities for layer 3 VPN, layer 2 VPN, and VPNless. But in the last decade, many things have changed. First of all, the real game changed for the industry. Ethernet has become the data link technology of choice, regardless of the field of application. Everything converged to Ethernet. It replaced all the old ones because it was able to economically scale in terms of throughput from the original 10 meg speed to the current 400 gig. The Ethernet plus IP MPLS technologies have become the foundation for every network. Once the physical data link and network layers were homogeneous, the industry started to target some simplification also at the control and service plane, or let's call it the overlay. And these efforts materialized in two new technologies, segment routing and Ethernet VPN. Segment routing can carry labels and provide fine-grained traffic engineering capabilities, replacing both LDP and RSVP without adding any new protocol to the stack. On the other hand, Ethernet VPN was originally born to provide a more efficient way to create multi-point to multi-point layer 2 transparent services, but it has come a long way since the early days. And today it can provide all the needed capabilities to replace any other technology to provide point-to-point, multi-point to multi-point, and layer 3 services using BGP as control plane protocol. And now, if you look at the new protocol stack, it looks a lot simpler, doesn't it? So let's take a deeper look to network services evolution. Service providers provide revenue-generating wide range of services, right? Such as E-line, ELAN, E3, multicast VPN, layer 3 VPN, data center interconnect. And these have traditionally been provided by different and disjoint VPN technologies, such as pseudo-wires, LTP and BGP-based, VPLS, LTP and BGP-based, next generation multicast and trap frozen, and layer 3 VPN RFC 4364. EVPN can be seen as the next generation all-in-one VPN technology that provides all these ranges of services in a uniform way. And we are witnessing a strong traction for this technology across all market segments: data center, enterprise, and service providers. Simplification comes to mind when you think about EVPN. Indeed, EVPN is largely considered as a unified control plane solution that applies to many data plane encapsulations: MPLS, segment routing, VXLAN, and VGRE. This unified control plane can provide multi-tenant E-line, ELAN, E3, integrated routing and bridging, layer 3 VPN, and EVPN gateway interrupt services with one single multi-protocol BGP family, SAFI 70, using just 5 different route types. So by using one single address family, it's possible to get rid of all the other control plane machineries to provide the same set of services. And as I said, EVPN can be used across domains. It can be used to provide infrastructure layer 2 and layer 3 VPN services, or to extend layer 2 and layer 3 services between data centers, as well to provide various business point-to-point and point-to-multipoint Ethernet connectivity and layer 3 services, as traditional vendors are doing today with IPVPN, VPLS, and so on. And finally, EVPN can also be used in a telco cloud environment to extend services within the data center and to the WAN. So what are the benefits of EVPN? Although having a single control plane protocol based on BGP providing different VPN protocols can be a compelling driver, it is not the only reason why so many major networking vendors and customers are currently embracing EVPN. First, EVPN is all about BGP and its benefits, being a well-known standard, interoperable, and scalable protocol. Using only BGP, there is no need for a separate control protocol for pseudo-wire signaling, like LDP. And of course, we can use BGP fast convergence techniques called BGP peak, prefix independent convergence. Another benefit is its efficiency. Providing all active multi-homing and not just dual homing, EVPN provides unparalleled flexibility where a multi-home device can be connected to n number of PE devices, and a PE device can participate in dual homing, triple homing, quad homing simultaneously. On the other hand, it offers fast convergence upon link or node failure by withdrawing a single route associated with each failed Ethernet segment, regardless of number of MAC or IP addresses sitting behind it. This feature is referred to mass withdrawal in EVPN. It also offers efficient fabric bandwidth utilization with better scaled ECMP support. And finally, EVPN is a flexible technology that provides the ability to provide both layer 2 and layer 3 VPN using a common technology, simplifying operations even across domains. And as EVPN is based on BGP, we can leverage BGP's power to apply fine-grained policies. So that brings us to the next section, and a quick pause to see if there are any questions.
Yes, so we've got a question here. Could you elaborate what the EVPN gateway function that was mentioned in the previous slide is referring to?
Yeah, great question. I did not mention too much about it. So it is a feature Arista recently delivered called EVPN interworking with IPVPN. And it provides the ability to do stitching of VXLAN or MPLS-based EVPN to IPVPN in a single box, providing layer 3 interconnect between both domains, doing both BGP address family and forwarding plane translation. So this can be very useful for a data center or a telco cloud, where instead of provisioning a PEC handoff between the IP fabric border gateway leaf and the PE routers, we can collapse the PE function into the border leaf. So using this feature, it provides the ability to simplify the operations by having a single device solution to form that demarcation between the data center EVPN domain and the MPLS core network domain, while also maintaining the multi-tenant logical networks across both between the data centers and the core.
Thank you. Great.
Yeah, perfect. Okay, so let's move on to the transport evolution with segment routing. So more and more operators have made a concerted effort to simplify their networks and eliminate the dependency on a wide set of protocols. Also, for many years, one of the biggest challenges in the network design has been effectively managing traffic flow end-to-end across the network. Stated more specifically, how is the traffic intelligently classified and path engineered throughout the network? Or how can the traffic be classified into differentiated levels of service without adding unnecessary complication to management, control plane, and data plane state in the critically important part of the network? there is a requirement for more flexible control plane on steering of the traffic flows at a much greater scale. We also see an increase on network designs that inherently have more eCMP. The ability to perform MPLS eCMP routing is very limited with traditional MPLS traffic engineering approaches. Finally, as native IPv6 deployments increase, there is also a need for a native solution for IPv6 networks and IP backbones that provide the same capabilities as current MPLS networks. Segment routing is the technology that elegantly addresses this set of requirements across many different networking domains. So, what are the segment routing roots and evolution? The research and standardization activities on segment routing originated in the late 2000s, mainly with the goal of overcoming some scalability issues and limitations that have been identified in the traffic engineered solutions used for IP backbones. In the early 2010s, the IETF started the Source Packet Routing in Networking Working Group, SPRING Working Group, to deal with segment routing. The activity of this working group has included the identification of use cases and requirements for segment routing. Currently, segment routing is receiving a lot of interest from operators for its applications in different types of networks: transport backbones, access networks, data centers, 5G networks. And this can be demonstrated looking at the very large number of patents that have been registered, around 13 RFCs and 51 internet drafts. So what's the basic philosophy of segment routing? Segment routing is based on the loose source routing concept. A node can include an ordered list of instructions in the packet headers, and these single instructions are called segments. So a packet can carry a path encoded as a list of segment IDs or seeds, so the state is no longer in the network, but in the packet. These segment IDs get advertised by each node using standard routing protocol extensions, ISIS, OSPF, or BGP, eliminating the need to run additional label distribution protocols, simplifying the MPLS control plane. And it has a native way of implementing traffic engineered paths that take advantage of eCMP behavior of IP. Finally, as we know that most of the times we will be dealing with existing brownfield networks, segment routing allows coexistence with the existing protocols for a smooth migration. So let's briefly look at how segment routing simplifies transport protocol stack. As you can see in the slide, with a segment routing based approach, the need for LDP for label distribution and RSVP for traffic engineering and fast reroute is eliminated, making the implementation simpler. Also, an external SDN controller can be used to drive traffic engineering decisions around path computation and reoptimization. And this is a very attractive solution and provides the perfect paradigm for intelligent, software-driven source routing. So let's look at the segment routing operation. Segment routing divides the network into segments or topological subpaths, and source routing is enabled, so a packet is transmitted from source with a list of segment IDs or seeds. There are different types of seeds and can be either globally unique, prefix seeds, or locally significant, adjacency seeds. A prefix seed is associated with an IP prefix. The prefix segment steers the traffic along the shortest path to its destination. A node seed is a special type of prefix seed that identifies a specific node, and it is configured under the loopback interface. In this diagram, these are the blue seeds. Adjacency segments, on the other hand, are the locally significant green segment IDs in this diagram, represent a specific adjacency, such as an egress interface to a neighboring router. Only the originator inserts the label in the forwarding table, and path state is in the packet header. So this is a natural fit for an optional controller computing and programming traffic path and imposing them at the source. In this example, we want the traffic to 6666 on the right not to follow the shortest path. and follow the path depicted in purple. So the controller will signal the path, and the ingress router will push 3 labels into the packet. When the packet gets to router 4 with its node seed and then local adjacency seed 45, it will pop both labels, and then get to router 5, who will also pop label 6, arriving traffic to node 6 through the signal path. We said that segment routing can easily interwork with existing LDP deployments. So with LDP, a simple mapping of SR to LDP labels is configured, as illustrated in the diagram. SRMS, or Segment Routing Mapping Server, is a router doing the interworking and will create an SR node seed label for a non-segment routing router, in this case, PE3. Segment routing routers now will install the proxy seed label in the LFIP as advertised from the router originating the proxy seed. As an example, we see that if P1 wants to send traffic to P3, FEC 11110, it will push 2 labels, label 601 pointing to SRMS, and then label 700, proxy seed of 700 assigned to FEC 11110 by SRMS. This makes interworking between SR and non-SR domains simple and scalable, allowing a migration path for operators dealing with existing brownfield networks. Okay, so control plane operations are needed to complement the data plane functionality and provide a complete solution for segment routing. The control plane can be based on a fully distributed approach in which the routers are capable to take independent decisions to set up and enforce the segment routing policies, or it can rely on a centralized segment routing controller that takes decisions and instructs the routers following the SDN principles, or on a combination of the two approaches, a hybrid solution. We observe now a trend to focus on a hybrid solution in which distributed routing protocols coexist with an SR controller. In this light, the segment routing architecture can be deployed by seeking the right balance between the distributed and centralized control. The distributed control is used by the routers to exchange reachability information and then evaluate the shortest paths in the traditional way, with no need to interact with the centralized controller. In this case, path is computed locally. But we need a centralized approach with an external path computation element to take decisions about the segment routing policies that implement advanced features or services like traffic engineering, VPNs, or service function chaining, ideally using an SDN controller. The mechanisms and protocols for the SDN controller to enforce segment routing policies by configuring the nodes are left open in the segment routing architectural definition. Some options are BGP labeled unicast and BGP SRTE, or even use a custom agent using EOS software development kit libraries to program SR multi-label stack tunnel mappings. The main characteristic of the segment routing solution compared to other SDN solutions is that only the edge nodes need to be configured to enforce a given SR policy, while the internal nodes do not need to keep state per SR policy. These features gives us substantial improvement in terms of scalability. Finally, static provisioning is also possible, configuring a route pointing to a label stack via the CLI or use extensible APIs in EOS to push a label stack. Okay, so let's take a look at the different use cases for segment routing. The first one being MPLS service and simplification. With the traditional MPLS approach, we could simplify P-core nodes by removing the need for large routing and forwarding tables. Now, the simplest way to leverage the distributed segment routing label state in the network is for traffic to follow the IGP shortest path while leveraging ECMP through the network. In this case, an ingress LER will simply push a segment routing label onto the incoming traffic corresponding to the next hop towards that destination. The main benefit with this approach is that an additional label distribution protocol like LDP or RSVP is eliminated from the requirement, making the implementation simpler and reducing risk in day-to-day operations and management of the network. But if we add to the mix a native IPv6 support, no need for 6PE or LDP version 6, and topology-dependent loop-free alternate, TI-LFA, as its main solution for fast reroute, we have great benefits over traditional LDP-based network. And that leads me to the second use case, which is topology-independent LFA. For a couple of decades, MPLS traffic engineering has been successfully used for a quick switchover to pre-computed backup paths, known as fast reroute. Segment routing provides topology-independent loop-free alternate, TI-LFA, as its main solution to fast reroute, bringing 100% topology coverage, simplicity, and path optimality. Compared to LDP, there are no targeted LDP sessions to manage and maintain with segment routing. And unlike LDP, it provides failure coverage even in ring or complicated partial mesh topologies. One can even argue that TI-LFA is superior to the backup link protection provided by RSVPT. In RSVPT, if a link fails, the protecting LSP will reroute traffic to the protected next hop, which often tends to be the suboptimal path. This does not happen with TI-LFA, as the backup path for a link always just follows the optimal IGP-based path, assuming the failed link is out of the topology. And the third use case is traffic engineering. So for a couple of decades, MPLS traffic engineering has been successfully used to supplement link state IGP control plane and provide routing based on administrative and bandwidth constraints. MPLS-TE uses IGP, ISIS, or OSPF to advertise topology, various link attributes such as configured administrative constraints, available bandwidth, etc., and RSVP to signal MPLS labels hop by hop, yielding to an end-to-end LSP, which can be used to steer traffic via a path other than the IGP calculated shortest path. The fact that each label switch router, LSR, in MPLS-TE must maintain the state for each LSP it originates, terminates, or act as a transit point for leads to a serious scalability issue. Various optimizations have been done in an attempt to solve this problem, and they solve the scalability problem to some extent, but increase the network complexity. Segment routing addresses some of these challenges by taking an SDN-centric approach. So instead of calculating path and encapsulating the source routed explicit path in the control plane, it defines the traffic engineered path as a list of seeds encapsulated in the data plane. Only the edge or ingress routers, LERs, impose the traffic engineering path as a stack of MPLS labels, thereby leaving the core free of per flow control plane state. This can be done using external SDN controller to drive traffic engineering decisions around path computation and reoptimization, utilizing parameters like distance, available bandwidth, latency, cost of long-haul links, and business logic into the path computation algorithms. So let's take a look at the SRTE use case for one optimization, where we have an external controller computing the path. On the one hand, basic topology information and additional information for traffic engineering need to be conveyed to the controller. The SDN controller can receive this information in different ways. For example, it can participate to the IGP routing protocol, or it can also receive information by routers using extensions to BGP link state. EOS also offers rich real-time state streaming telemetry solutions to export various states from the platform to an external analytics engine. This allows customers to enhance their TE decisions and enables troubleshooting to changing conditions in the network. Whatever mechanism has been used to retrieve the needed information from the nodes, The SDN controller is in charge to take decisions about the SR policies that implement advanced features or services like traffic engineering. So how are these decisions transmitted to the network imposing the path computer label stack? Here I will talk through a couple of approaches. The first approach is the one on the left, based on Arista EOS software development kit. Arista EOS is built on the foundation of programmability and with the philosophy of allowing customers to develop their own software on this platform. Using EOS SDK, customers can develop their own customized EOS applications in C++ or Python. This EOS development model allows third-party applications to be first-class citizens of EOS, along with other EOS agents. One of the highly leveraged use cases of EOS SDK is for MPLS segment routing deployments, where the custom agent uses EOS SDK libraries to program SR multi-label stack tunnel mappings using MPLS next hop groups at the LER. With this approach, customers can develop their own control plane in the agent, interact with the external controller to accept multiple tunnels, build health checks for tunnels, and notify the controller of failures. On the figure on the right, we have another example where we also have a centralized external path computation engine or controller. But in this case, the SR tunnel TE paths are signaled dynamically using a protocol like BGP-LU or BGP-SRTE. BGP label unicast is defined in RFC 3107, and in brief, it means that BGP can advertise unicast routes, like IP prefixes, with associated MPLS labels. Okay, so BGP-LU can be used like any other BGP peering router to router, but can also be used between routers and a controller as a way to program static routes with labeled paths. So while BGP-LU uses a mapping of next hops to segment lists to enforce these segment routing paths, BGP-SRTE uses BGP segment routing policies to enforce segment routing paths. An SR policy is identified by a two-tuple of color, which is an extended community, and endpoint. This is the use case that I will be demoing later in the presentation. So the last use case is egress peering engineering. And this is the perfect use case for large CDNs with numerous exit edge routers using scale-out leaf-spine design tiers to connect these edges to the cache nodes. In order to scale bandwidth, they use source-based traffic steering to control exit point and or a network-to-network interface, the peer link, with no impact on BGP ASVR design. Okay. But this is also useful in an SP environment, as a typical SP has multiple peering relationships with multiple other SPs. These are usually geographically distributed, differ in number and bandwidth, and use various business or cost models. Traditionally, service providers use a policy to manipulate the BGP attributes in the prefixes received from a peer, which may result in suboptimal decisions. With segment routing, we have the ability to distribute traffic among several egress links based not only on destination address, but also by considering the ingress ASVR or ingress port, even originating node or host, providing much finer granularity and also bandwidth management. This is especially true if we combine it with traffic statistics and centralized optimization. So how can we scale bandwidth in these environments? First, we will ensure that all peers are used irrespectively of topology change, link or node failure. And using bandwidth community hashing towards all peers will be handled by an equal cost multipath. Then also we can enforce the egress link by assigning a seed to peer link, and the controller will program a label stack on ingress router, top of rack or server, including that seed. Just to mention that our solutions are all standard-based, and we participate at EANTC multi-vendor interoperability tests. This year, we ran 20 successful tests, including EVPN and segment routing, with one single box based on merchant silicon hardware and one single OS. To summarize, before we head into our demo, let's review segment routing benefits. It uses existing MPLS data plane and services, but drastically improving MPLS control plane with simplicity, with less protocols required, such as LDP and RSVP, with scale, as per flow states are only maintained at the ingress edge router, and with the CMP support, and centralized optimization and automation. It provides IP fast protection for any topology in a simple manner, as well as native dual stack support. And finally, it is a standard-based protocol with strong operator adoption and involvement. Okay, so before I dive into the demo, let me pause to see if there are any questions.
Yes, so we do have a question here, and the question is, let me read this. So what type of services do we support with our segment routing TE policies?
Okay, so yeah, great question. Yeah, so traffic steering into SRT policy is supported not only for IP unicast services, but also for 6PE, MPLS layer 3 VPN, layer 3 VPN, EVPN VPWS, and also LDP-based to-the-wire services. And in September, we should support also L2 EVPN services. So a broad range of services.
Okay, thank you very much.
Okay, so let's move on to the demo. So in this demo, we will be showcasing a link core using ISIS segment routing, using Arista 7280R R2 100 gig Broadcom Jericho-based fixed format routers. We will visualize live traffic feeds via CloudVision portal telemetry, and we will leverage external open source tools. On the one hand side, SFlowRT as an open source SFlow controller, and on the other side, we'll be using ExaBGP and YaBGP controllers to program traffic paths, taking advantage of BGP labeled unicast and BGP extra policies. Okay. So let's get started with the first demo. Okay. So in this first demo, we will demonstrate manual provisioning of SR paths using ExaBGP with BGP labeled unicast signaling. So BGP labeled unicast, using BGP labeled unicast, you can compute a path of line, like on a controller, and push to an edge router that's running an active ISIS segment routing network, which is the case. And what it does is to distribute MPLS tunnel paths through BGP. And these labels are carried as the part of the NLRI information. So we have this diagram, okay? Here we have our controller. We have a customer red connected to P1, customer blue connected to P2. Customer red is receiving prefixes from 5 prefixes from customer blue, and we are sending traffic initially following the shortest path, okay? Because we first push a static 96005 MPLS label to P1 via ExaBGP using BGP label unicast, okay? And that label is associated with P2. That's the node seed of P2. So we will follow the blue line, okay, via LSR1 and LSR2. So we will be altering the path, pushing a new MPLS label path, okay? Which with that, we will the old ELF inventory will be withdrawn, and the new path will be pushed from ExaBGP via BGP label unicast. And this will be seen in CloudVision telemetry application, okay, how this path is being altered. So let's get started. We are running, here we see that we are running ISIS segment routing, okay. And well, we have IBGP between the Ps. We are associating different node segment IDs to different loopbacks of PEs and LSRs. We do have a BGP labeled unicast neighborship between P1 and ExaBGP controller, as we see here, just like a normal BGP session. We see that we have BGP labeled unicast routes, 5 routes, okay, with node seed 96005, okay, and that is following the shortest path. We see, yeah, this is the tunnel information with label 96,005. And now here we have a script monitoring different interface counters. Okay. And in the Cloud Vision telemetry app, we can see that there's no traffic going through LSR3 and LSR4. Okay, the traffic is going directly through LSR1 and LSR2. So let's make the path change. Okay, first of all, we'll withdraw the 96,005 label that we added initially. And then we will enter a new segment list. Okay. First, we will withdraw this tunnel, okay, the label 96,005, and then we push the new label stack, and we see that the new label stack tag is pushed and the traffic path is being altered. If we look at the interfaces here on the right-hand side, now we see that there's traffic on LSR3 and LSR4. So the new path is P1, LSR1, LSR4, LSR3, LSR2, P2. And if we look at the Cloud Vision, we also see in real time that right now there's traffic going through LSR3 and LSR4. Okay. So in previous use case, we demonstrated manual provisioning of segment routing paths using XABGP. Now let's move on to the second use case, where we will be using YABGP controller, but this time alteration of traffic path is done automatically when traffic rate between LSR1 and LSR2 exceeds 85%. Okay, so this is the same topology diagram, okay? In this case, P1 is learning the same routes as before, but this time with a BGP community value, okay, which is the color, okay? We'll see that. Okay, so first of all, we will be pushing static MPLS label with all 5 communities, okay, and the traffic initially will be flowing through the blue path. We have LSR2 streaming S-Flow analytics to the S-Flow RTE server so that you can check the utilization of this link. So we have a script that makes RESTflow API calls to monitor interface between LSR1 and LSR2, and we'll be identifying the top talkers. If the link bandwidth exceeds 85%, the script dynamically pushes a new MPLS label path for a given talker flow based on external extended community value, the color. Okay. So what it will do is the script will be pushing a SR policy via the YABGP controller to P1 for traffic destined to the top flow IP, following the orange path. Okay. And of course, we'll see the traffic change, then the altered path in the Cloud Vision telemetry application. Okay, so in this case, we see that P1 has an SRT neighborship with the YABGP controller. We are learning the routes from customer blue, and in this case, they are being tagged with the extended community value, which is the color. We are learning routes to customer blue prefixes via ISIS segment routing tunnels, okay? And we are pushing label 96,005 for that. And we have this Python script identifying the top flow when traffic rate is above 85%. Okay, we check that before making any change, the traffic is following via LSR. There's no traffic via LSR3 and LSR4, okay? So it's following the blue line. So we push more traffic to cross that 85% mark on a specific destination. So we see that the traffic increases up there, okay? And the script kicks in automatically because traffic is above 85%, okay? It identifies the top flow, okay, which is prefix 1511 with color 500. And it's pushing the SR policy, okay? That's what it's doing. It's not yet pushed. Okay, and now the policy is successfully pushed, and we see that for that prefix, we do have a new label stack associated, okay, via SRT policy. And we see traffic going through LSR3 and LSR4. So the traffic flow has been altered. And we can see that in real time with our vision telemetry app as well. Okay, so that brings us to the end of this presentation, and let me summarize what we saw today. So during this presentation, we talked about simplification of the control plane, as well as the state in the network with segment routing and EVPN. Arista offers a breadth of feature set, including features that will ease the migration. As a pioneer in the networking industry, Arista has now committed to using commercially available merchant silicon from multiple suppliers across its portfolio. This simplification accelerates the adoption of merchant silicon to achieve platform efficiency, providing the most dense fan-out inside space and power-optimized form factors to achieve the needed efficiency to scale out the infrastructure. Adopting the merchant silicon model for hardware innovation allows Arista to focus on a greater majority of R&D resources on software development and its next generation network operating system, EOS, with a quality-first approach. This enables streamlining with operational efficiency via a single operating system end-to-end across all routing deployments. This simplicity in software and hardware, together with the programmability and real-time streaming telemetry, enables operation efficiency and common automation framework, thus cloudifying service provider networks, accelerating service delivery and innovation. So with that, we are at the end of this webinar, and I would like to thank you all for joining.
Thank you very much, Iteso, and thank you all for your attention over the last hour or so. I hope you found that interesting and useful. Just a brief reminder that we do have 2 more sessions within this series. So next week, same time, on the 7th of July, we'll have Arista Service Provider building blocks. And then the subsequent week, on the 14th of July, we'll be going through some next-gen service provider use cases where people actually using some of these innovations in the field. So hopefully we can see you again. And thank you once again for your time and attention, and enjoy the rest of your week. Thank you very much.